robust and elegant solution to the client's requirements. We have a bigger board for a central processor, a low-level interface board for controlling the motors and RPM, and a wireless communication system using XP radios. We've developed a custom version of the Gen 2 operating system. This is a lightweight, power-efficient solution and simple. This means that we're only using 20% of the CPU of the bigger board. Compared to people using OpenCV, they will be using about 80% of the same board. We're able to get 30 frames per second. This means that we can see everything on the track and make smart decisions and safe decisions about which lane to go into and how to stay within the lane. As well as our USB serial communication is custom. This means that we have very reduced latency, so any design decisions made on the bigger board gets implemented right away on the system. Our system is also very modular in design and very portable. We can run it on a bigger board, we can run it on a laptop, we can run it on any system practically. Our system is also integrated. Everything works as is. There's no like person pressing a laptop button and then running a different setup.
So I'll be talking about the budget. So we have come up with a very affordable autonomous solution. Given the client's budget of $750, we're able to come up with a solution using only 66% of that, spending a grand total of $500. And I'll be talking about the design process as well. So the simulations we came up with provide a proof of concept to test the various methods of lane detection and following during the design process. In the first simulation we have here, we use a high-level concept to calculate midpoints along line segments on both straight and curved lines. And we transferred that onto real image processing using the MATLAB image processing toolkit. So using this toolkit, we applied different filters to isolate the lanes, identify them individually, and also mark the midpoints using the previous simulation that I showed you before. With MATLAB at our disposal, such a very powerful tool, it reassured us that the hardware implementation that we had would be sufficient to complete our requirements. And we translate these algorithms to our implementation in C++, which Hector will explain.
Okay. So as Mohan was saying, the proof of concept we tested in MATLAB, we implemented then in C++. The reason we implemented in C++ as opposed to using other package tools like OpenCV and other groups did is for efficiency and for customizability. So basically what Steven was saying, we're only using 20% of the BeagleBoard's capacity. That's due to the fact that we're taking information straight from the video driver, processing that, and then giving it the decision code. All that is custom made. We wrote that all ourselves. So the first thing that happens in the image processing is that it separates what it sees in the image into lanes, obstacles, or noise. Okay? Now it stores these and it sends it to the decision code. So first I'm going to describe what happens in lane following. So in lane following, we get the lanes from the image processing and we calculate the midpoints. Okay? With these midpoints, we correct path deviations relative to these midpoints. So we know where our car is relative to the midpoints of the lane, and we correct our path relative to these midpoints. What we're doing is we're looking into the future. So we're taking several midpoints in the future and correcting the path accordingly. We actually have implemented a proportional integral controller, where the correction we have on our wheels during our lane correction is proportional to the deviation we have from the midpoints. So this provides a really smooth lane following. Another thing we do is we do a weighted average. So midpoints closer to the vehicle have a greater impact on the correction than midpoints that are further from the vehicle. Now this provides greater stability at higher speeds. Okay. Now you might be wondering why we chose camera versus a line scan, because that's basically the two implementations that are available right now. The reason being that in the camera we can do much more predictive things. So we can look much further ahead as opposed to line scan. You only get to see that one line and you can only make decisions in real time. With the camera we can look ahead and do predictive things. So if we want to go really fast or something, we want to implement this, we can expand it into something much more predictive. So we can start turning a lot earlier if we wanted to. Yeah, and that's room for expansion. So now we're going to demo the lane following. Go to Colin.
All right, so here we have our car sitting in the outer lane, ready to go. When the car starts, it doesn't actually know perfectly where it is on the track until it's seen 3 lanes. So in this case, the car has only seen 1 or 2 lanes, but it's able to maintain its position in the correct lane, even as it sees more or fewer lanes, because it keeps track of that. As we go along the outer bends, we only see 1 lane with our camera. All right, so, and then we'll go in the reverse direction. To do this, we have, through our remote, we set it to let it know that we have changed its locations, and it does the same thing again. It starts on knowing exactly where it is, and it makes and updates its estimate of where it is as it goes around the track. And that's the inner lane. Back to you.
Okay, so now I'm going to describe what we're actually doing for obstacle detection. So this was, as you might suppose, significantly harder to do than lane following, particularly because our code is running simultaneously. So we're processing the entire image and processing both lanes and obstacles at the same time. So the filters and the tricks we use kind of tend to interfere with each other sometimes. So that was kind of tricky to overcome what we did. So the first thing we do when we receive an obstacle from the image processor is check if this obstacle is in the lane. Because we can see obstacles outside the track, but we don't really care if they're there, because we only care about obstacles inside lanes. The next thing we do is that if there's an obstacle inside any particular lane on the track, we reduce our speed. So why we implemented this is we wanted to make it more realistic. Generally, when you're driving and there's no cars on the road, you tend to go a bit quicker than if there are cars on the road, regardless of if they're in your way or not. So we lowered our speed regardless of if we see an obstacle. Next thing we do is we determine, as Matt was saying, which lane we're in. In order to make intelligent decisions in lane changing, we need to determine which lane we're in, so we can know which lane we can go to and which lane the obstacle is in. After that, we calculate the distance to the obstacles. Now, the way we're doing this is quite convenient because we're using the same algorithm we used before with the midpoints in the track, and we're just counting the midpoints towards where the obstacle is, and that gives us a very accurate distance. After that, we compare what the scenarios are. So we see multiple obstacles on the track, right? And we can compare this to a complete set of scenarios we have and decide, and then it decides based on what we tell it to decide when the scenario occurs. If the scenario requires a lane change, then we make the lane change as necessary. So as Matt was saying, when we decide to change a lane, we don't just do this hard-coded. We don't just move to the right or move to the left. What we're actually doing is we're measuring the deflection of the track ahead of us in order to compensate for the turning angle we need. So logically, if we're, for example, if we're right here on the middle lane, and as it's going forward, you see how it turns there? It's not going to be the same amount of turning angle that if you were turning to the inner lane, because you're on the turn, right? So we account for that by measuring the deflection as a vector in what we like to call car space. After that, right. So you might be thinking why we use the camera as opposed to sensor-based. There's several reasons for this. One, the camera isn't as geometrically limited as sensors. So you could probably ask the other groups, and there's quite a bit of tweaking that goes on as to pointing your sensors in the right direction. There's a lot of tweaking that goes on that. With us, we just kind of put our camera there, and whatever it sees, it sees. Another thing is that in the best case scenario that you're able to configure your geometry with your sensors, you can only see as many obstacles as sensors you have, right? Like it makes sense. You can't see 2 obstacles with 1 sensor. So you're limited by the amount of sensors you have, as opposed to a camera. It sees all the sensors that are, all the obstacles that are in the image. We can do much more intelligent recognition. So because we can look further into the future and we don't have a limitation on how many obstacles we can see, we can make much better decisions as to which lane to turn into. The next point is that our solution is more generic. The two sensors that are used in lane following and obstacle avoidance right now are IRs and ultrasonic. IRs are sensitive to the object reflectivity, and ultrasonics are sensitive to the object's geometry. With our solution, we only need to have the obstacle be as white as it needs to. Now, up to Matt to do the obstacle detection demo.
All right, so this has been running track just to see behind the scenes. So we're just going to set up the obstacles. All right, so we're starting in the middle lane back here. All right, and so we'll turn to the right and then back to the left to dodge these two obstacles. As it approaches to 3, it will stop. It's not just a trivial demonstration. And then we'll go to our obstacles on the curves. So in this case, we're again starting the car off in the outer lane. And again, we're C heading, so it doesn't know exactly where it is on the track and figures it out as it goes along. So as we approach this first obstacle,